right, I think we can get started. So we're excited to host Jiayuan Mao, who's visiting us from MIT. So she's a rising star in the field of using neuro-symbolic representations to solve the most challenging problems in reasoning, planning for computer vision, to robotics. And one fun fact that I found out today is that she's organizing 7 workshops just this year. So she's going to be busy. And they're in various places. NACL, ICML, ICRA, AAAI, CVPR. So she is really, I think, it shows her breadth and depth of her work. And without further ado, let's welcome Jiayuan.
Thank you so much. And yes, thanks everyone for coming. So my name is Jiayuan Mao. I'm a PhD student at MIT. So my research is really about trying to understand the structures of learning, reasoning, and planning problems with the approach what I call the neuro-symbolic concepts. So in my research, I use robotics as one of my primary test bed. So I'm going to begin this talk by asking this question. How can we build a general purpose physical intelligence system that is some system that can solve physical decision-making problems? I would argue one of the first options that we can consider is think about intelligence as fitting functions to data sets. So we start with some high-level understanding of, want to build a policy pie that takes in all the historical observation as an input, and an output what's the next action to take. With that approach, we can collect some data and try to build and train a function that approximates that thing from a data set. This is a video released by a company called Physical Intelligence recently. And then they are training their robot trying to fold a box. And then if you look at some of the technical spec of it, it requires 100 hours of training data for training the robot just folding this particular box. And if apply the same policy on a similar box, you get some success rate that is around like a 60%. So I would say this is in contrast to how humans could do. As humans, we can learn from just one single example and generalize very reliably to all different kinds of states and goals. If I show you this video about someone cutting a water bottle to form a funnel and use that to pour liquids, you can immediately generalize from this single example trying to apply this technique to a different bottle, to a different kind of liquids in completely different situations. The kind of task we want to do in real-world environments is very, very diverse. So think about housekeeping, right? You are constantly seeing novel objects in novel configurations you have never seen before, and given instructions that people have telling you, to accomplish different kind of things. So to really stress that, I want to show you this particular example, which is a little physical game. The rule is simple. There are a bunch of objects on the table, and you're supposed to pick 2 of them. Let's call them A and B. And you're going to hold them one with each hand and trying to lift up a third object C from the table without directly touching it with your hand. So this is a trial that a person can have, trying to lift up a glass using one pen and a cap on the other hand. So this is something that you probably have never done before, but clearly you have some ideas. And this showcases, how human can make flexible reasoning and planning, in this kind of novel scenarios, even with those objects they are already familiar with, in completely novel ways. So how can we get there? One proposal is to say, we just need more data. But will scaling really solve this problem? So this is a very challenging question to answer, but we have some ideas about the scaling law from complexity theory. So this is a result that I recently proved in 2023, which roughly reads, for transformer policies, its size should scale exponentially with the number of sub-goals that cannot be achieved independently. So I'm not going to give you, details about how exactly this thing works, but I'll give you some insights about it. So suppose that I want to build a policy for a particular task. If there's a way that we can factorize this high-level task into different sub-goals, where you have sub-goal 1, sub-goal 2, and sub-goal 3, and you can train policy for each one of them, and directly stitching them to solve the original task. If such kind of decomposition exists, then there is also a small policy for the original task. However, if not, you need to increase the size of your transformer policy exponentially. So to put this in context, if you consider the ABC pickup example that we talked about before, it's tempting to decompose this task into pickup A, pickup B, and pickup C. But actually, this decomposition won't work because the particular way that you pick up object A is going to affect whether or how you can later on use that to pick up C. So such kind of decomposition doesn't work. So this is a harder problem that requires to reason about the interaction between A, B, and C. So for people who are familiar with complexity theory, such kind of exponential bounds should be familiar to you. But what we are managed to do in this paper is we're identifying some fine-grained complexity theory using the number of dependent subgoals as a measure, and trying to connect that to neural network policy learning, and also having implications on the amount of data that is needed to do that. So if we hold the belief that scaling is not going to solve this problem alone, so how can we do it better? So in today's talk, I'm going to talk to you about my new paradigm of building AI that allows us to learn from one single example and then being able to generalize out of the distribution to novel objects, states, and possible goals by using the machine learning tools that we have, either large model or small model, with the reasoning algorithms that we know. So all this kind of thing starts with the following view, which is think about intelligence as world modeling and test-time inference. In the particular case, I will talk about planning. So let's think about a concrete example, which is I'm in a household environment. I'm going to clean the plate in a kitchen environment. One way to find such kind of sequence of action to accomplish the task is you think about doing tree search with a transition model. You start with some state representation of the current state. You enumerate possible actions you can take in this environment. You do that recursively until you have found a plan. So such kind of search and with transition model and test-time inference is definitely not new in AI. Actually, a lot of the recent success in AlphaGo, AlphaGeometry, which is a theorem prover for geometric problems, and also large language model chain of thought or tree of thought, if you have heard of those kind of terms, is all based on this kind of idea. There's an underlying assumption behind it, which is some kind of transition model which allows you to do this kind of search or test-time inference are more compact than the policy itself. So conceivably, it's more easier to be learned. But to really implement such kind of system, we still need to be careful about what kind of world model should we build. For example, one idea is just to build an end-to-end world model, saying like doing some pixel level prediction. And this is a recent result that I generated using OpenAI Sora, one of the state-of-the-art model, doing video prediction. I prompted it to generate a video showing a robot is cleaning up plate. Okay, so this is the video it generates. So first of all, it's not physically feasible, and also it actually doesn't complete the task as I instructed. I want to highlight there are two important challenges here. The first one is how can we scale up such kind of model training so that they can become physically feasible? And second of all, even if we have such kind of model, how can we efficiently use them for planning purposes? So to address those challenges, my research focused on learning a different kinds of model based on the principle of learning abstraction and compositional world models. So again, focusing on this kitchen environment, as humans, we can see there are all different kind of entities in the world. There are robots, there are different kind of objects. And an object would have different features, like they have shapes, poses, or dirtiness degree. If you think about actions, they connect, they're related to certain aspects of the thing, a few objects in the environment, and then the effect of that is going to be changing certain aspects of the environment, like joints, or will change the pose of an object, change the dirtiness degree of an object if you execute this wash plate action. So in today's talk, I'm going to tell you, how can we build such kind of a model using this framework, what I call neuro-symbolic concepts. So I'm going to tell you exactly what I mean by neuro-symbolic concept in just a minute. But for now, think about these concepts are compositional abstractions over states and actions. It's living in like an abstract space. It's something you can see in vision, something you can talk about in language, and it's something you can act on. So it's really a representation that connects important areas in AI, vision, language, and robotics. And then the overall goal is to build systems that can do very efficient learning from one or very few examples and generalize out of distribution. Here's the overview of today's talk. I'm going to start with, what do I mean? What is a neurosymbolic concept? I'm going to give you some example in vision language understanding. And then I'm going to talk about one-shot learning of generalizable actions. And then finally, I'm going to talk about learning for long horizon plans, which is really an area that bridge vision, action, and language representations. So now I'm going to get into what are neurosymbolic concepts. So mathematically, Neuro-Symbolic concept, they form a compositional and abstract world model. It has two parts, some state features we care about and some action models. I'm going to use this particular way to represent state features. They have some ID, such as feature 1, feature 2, and feature 3, and they are associated with some entities in the physical world. Usually, they will associate with a neural network-based extractor that can recognize those features from the raw perception data. You can also build relational features, such as a relation between two entities. For actions, I'm going to use the particular way to represent it. It's going to have some precondition. Some condition must be hold true before I can execute this action. It will have some body which actually moves the robot to accomplish this task. And finally, having some effects, which is how it's going to change the state features. So people in the past have been trying to build such kind of model, but there are some lessons that we learned which are kind of like bad practices. This includes building a fully discrete model, which is not able to capture the continuous nature of the world. And also, a lot of the earlier work heavily rely on human-defined model, like human telling the system what are the important features. And also, human needs to collect fine-grained examples or fine-grained annotations to teach the robot how to recognize each individual feature. So those kind of things make the entire learning not very scalable. Today, I'm going to talk an alternative way to build such kind of representation, which I call learning neuro-symbolic concept from language. So it starts with thinking about those entities being physical primitives that we can talk about, like objects or events or robot commands. And build on top of that, we think about those names and the way that those features, the concepts relate to each other. They are obtained from language, so they're termed with language. The key inside here is all those kind of symbols that would define a compositional structure of concepts about the physical world. And then it allows us to build learning systems that are with minimal human priors and without dense supervision for any of them. So in the following, I'm going to concretely ground those ideas in a particular example of visual question answering. So this is some work that I've been doing, actually during my undergrad almost 7 years ago. So this is by no means a state-of-the-art approach trying to solve visual question answering problem. But this kind of work really shows what do I mean by neuro-symbolic concept and some of the basic idea of how to learn them from language data. So the problem is the following. So you give an image and you give a query, a natural language query, like is the plate on the counter. You want to build a system that can answer this question. One of the standard practice is you say, I build an end-to-end neural network that takes in the image and also the query as input, and output was the answer. So in this framework, there are two things entangled in the learning problem. The first one is the learning problem of those concepts, like how to recognize shapes, relations. And the second one is some reasoning capability, such as how to count a number of objects. So this brings the limitation of, first of all, you usually require a lot of data trying to train such kind of network. And second of all, after learning, these concepts do not exactly transfer well to other tasks. Based on the principle of neuro-symbolic concepts, now we can have a disentanglement between concept learning and reasoning. So it will start with parsing this natural language instruction into a symbolic program that recovers the underlying reasoning chain of it. For example, in this case, it can be decomposed into 3 different steps. The first one is we want to find an object that is a counter. And then we want to find an object x, such that x is a plate and x is on top of the counter that we just found. And then we want to find if such kind of object x exists or not. This particular step is called language parsing or semantic parsing in our P community. And then the state of the approach to solve that is just by using large language model to generate code. So this is not really the focus of today's talk. Such kind of program can be visualized in this diagram, having 3 steps. And then there will be a bunch of concepts, in this case, the state features related to that, like counter or plate, and the relationship on. So now we're going to focus on this like a visual diagram representation of this program. So after obtaining such kind of program, one thing we can do is that we can do a differentiable execution of this program based on the visual scene representation. We first do an object detection to localize all the objects in this environment. And recall that here, the counter is basically a state concept and it's associated with a neural network that takes in an object feature as input and output a yes or no. So if you apply this counter neural network on top of the feature of each individual object, you will get a score for each individual object being a counter or not. And think about it as a probability or a confidence score being each object being a counter or not. You can do a similar thing for recognizing relationship between all pairs of objects, and you can compute what's the object on top of the counter by using this chain rule in probability, the probability that x is on top of the counter equals to the summation over y, such that y is a counter and x is the top of y. You can do similar thing applying the plate recognition network on all the objects, recognizing where the plate, taking a conjunction of two sets, trying to find objects that is both on the counter and also is a plate, and then return the probability that such kind of object exists or not. So one thing to be seen is that this final output is basically a composition of all the intermediate probability values that I have generated by applying those neural networks on top of the visual scene representation. So this means that the entire computation graph is actually differentiable with respect to all the intermediate probability values, and subsequently to all the neural network weights. So this means that as long as I have the answer to the original question, in this case, yes, I can directly use that as the supervision and just use standard end-to-end differentiable training to update the weights for all those little neural networks that recognizes counter, recognizes on, and recognizes plates. So the important feature of this framework is that, first of all, you don't need to manually annotate what are the concepts you want to learn, because fundamentally they come from all the questions in your data set. You can use a language parser to parse them into programs and extract all the concepts you want to learn from data. And second of all, you don't need to manually annotate, this object is a counter, that object is a plate, but instead, we just rely on paired question and answers to automatically do differentiable learning of all the recognition network for recognizing counters on and plates. And then the execution trace here is a combination of neural network execution and some symbolic operations, like taking conjunction of two sets or counting the number of objects. So as a consequence, such kind of system is usually very, very data efficient because it really disentangles the concept learning problem and the reasoning process, where the reasoning part, like accounting, can be just manually coded as deterministic programs. So this kind of system is usually much more data efficient than other methods, no matter whether it's neural or like a neuro-symbolic alternatives. They're usually 10 times more data efficient. And also the learned small concept networks, they can transfer across different tasks. You can use them for retrieval, for counting, for planning purposes. The underlying principle here is to use language, human and programming languages, to help you to disentangle the concept learning and reasoning. Such kind of framework is actually very general. We start with applying and developing such kind of system to two-way question answering settings. And then soon after we released the original paper and the code, people have been trying to extend this kind of thing to reason about dynamic things, like understanding events and their causal relationship in videos. And also to understanding 3D refrain expressions in point cloud data. And also recently to human motion capture data. So in 2023, my colleagues and I published a paper that basically talks about how we can integrate the large language model capability of understanding language, basically can translate natural language into executable programs with this capability of doing concept learning from very few data, so that we can build a system that can reason across all different kind of domains, including 2D, 3D, video, and also sequential data. And in the future, I'm very excited about applying similar kind of things to other areas, including areas where data efficiency and generalization plays an important role there, such as healthcare or biomedical data. So this gives you an overview of how can we learn concepts from paired images and the language data. So for the next part of the talk, I'm gonna slightly shift the focus to learning to think about modeling actions and then learning them from data. So for now, we are gonna put aside language a little bit, and then later on they will come back. So in this part, I'm gonna talk about one-shot learning of generalizable actions. So I want to first, go back to this original representation that we talked about neuro-symbolic action concepts. So we say an action is represented as a precondition, a body, and also an effect of it. So for precondition effects, you can think about them they are defined on top of state features. But we haven't talked, very detailed about, how should we think about the body of it. One of the straightforward ways to think about it is you say, oh, it's just a policy that maps from current state to the next action to take. But actually, I have already hinted you, actually, policy-based representation is not very good because they're not composable over time. So going back to our ABC pickup example, if you have 3 different policies, one for picking up pen, the other one for picking up the cab, and the third one for pivot the glass, actually, they are not directly stitchable to accomplish the original task we're interested in. So in today's talk, I'm going to talk about an alternative way to think about actions and talk about learning and generating actions, which is think about generating actions by constraint optimization. I'm going to use a simple skill as an example. So let's think about pick up an object. So really the goal here about picking up an object is generate a trajectory of the robot, satisfy some path constraints, such as I want to stay within my joint limits, I want to avoid collision with other objects, and I have some sub-goals, like at the end, I want to be holding the target. So an important feature of such kind of constraint optimization view is now you can compose actions temporally with a global constraint optimization framework. Now, if you say, my goal is to pick up the plate and then place it onto a dish rack, you still have the same set of path constraints. Like I want to avoid collision, I want to stay with my joint limits. I will have one sub-goal, which is I want to be holding the target. Another sub-goal, which is the plate is on top of the rack. So this problem can be written as a slightly bigger constraint optimization problem, which is given the original state S. I want to find two trajectories, T1 and T2, corresponding to two parts, two segments of my trajectory. And then, also two states, S1 and S2. Minimize some cost. In this case, let's just say the overall length of my trajectory. And I want to say, okay, I want to subject to the physical dynamics. Executing T1 starting from S0 give me S1. Executing T2 starting from S1 give me S2. I have some collision-free constraints over my trajectory. I have some sub-goal constraints. I want to be holding the target as S1. I want to continue holding the target through the until T2. And at the end, I want to have the object on the rack. So if you look at all those things, all the constraints written here, they can be categorized into three groups. First of all, we have some dynamics constraints. In this particular case, just rigid body physics. We also have some other constraints like geometric constraints. In this case, trying to avoid collision between the robot and other objects in the environment. There's some other constraints like task-relevant constraints, like I want to be holding the target at a particular position. I want the object to be on the dish rack. So such kind of compositional structure gives us a lot of leverage in learning. So first of all, now learning can happen at two different levels. In learning to solve a particular problem, we can say we can first learn what are the set of constraints we need to subject to. And second of all, for each constraint, how can I generate values that subject to that constraint? And second of all, we do not really have to rely on learning each individual constraints all from data. We can say for some of the constraints, we can rely on human-built physical models. In this particular case, let's say the rigid body physics can be implemented by a physical simulator. The geometric constraints can be implemented by some motion planners that humans have been building. And it's really all those task-relevant constraints that really requires to do additional learning from data on. To showcase this kind of framework in practice, I'm going to talk about a particular case study, which is how you can learn to hang objects from one single example. So let's say I have a reference video showing you how you can hang a hanger onto a rod. Now, I want you to apply the same skill to a different object, in this case a mug, and then onto a different object, which is a mug tree. So as I mentioned here, there are a lot of decision variables to be made, and then including the grasping pose, the hanging pose, and also the motion trajectory, and then they're all interconnected with each other. So this means there's a joint constraint among all of them. So in trying to address this problem, people have been trying to develop a lot of different techniques. One of them is called model-based planning. That is, I try to enumerate all possible contacts that can happen between my robot and the target. Like, think about different ways to grasp the target. And also think about all different kind of locations where can have contact between the mug and also the mug tree. And then just verify if they're successful or not using a physical simulator. So because the objects are usually have very difficult, very complicated geometry, this kind of approach is usually very slow. To address that, people have been proposing ideas such as unsupervised learning plus policy learning. So what they do is that they portray some feature representation based on a large data set of mugs. In this particular case, from this paper from Antonio, they're doing something like, we're generating 100,000 synthetic mug shapes, and we're training some representation on top of that. And then we're collecting very few examples, for example, one-shot example, and then trying to train a policy using that visual representation of the mug. And then they have some results like a 42% of success rate. Using the framework we talk about, now we can decompose the learning problem into two parts, learning the set of constraints to satisfy, and also learning values that satisfy these constraints. So in such kind of physical decision-making problem, the set of constraints you need to follow is basically the sequence of contacts being made in between the robot and in between different pairs of objects. And then here the values is really, where should I make those contacts, like the contact point. And I'm going to show you how we can make use of visual pre-trained models to achieve such kind of one-shot transfer of those kind of contact points. This is how this kind of system, put into practice. So we're perceiving those novel objects and in a novel scene. And then we have our reference video, in this case, hanging the hanger onto a rod, and we're seeing the new object using an RGBD camera, so we get a 3D shape representation of it. What we do is we're trying to use visual pre-trained feature, trying to find the corresponding point between the contact point happening in the training video, in that reference video, with all the points on the novel objects. In this case, you can think about those highlighted areas in the heat map. They highlight areas which have local geometric shapes, similar to the contact point you see in the training time between the hanger and also the rod. And here we're using some very generic visual pre-trained models, in this case DynoV2, to do that. So such kind of visual feature is actually very noisy, so we can see that there are a lot of areas that are being highlighted but not really corresponding to the right part they want to do the hanging motion. So what we do is that we're using such kind of thing as a guidance for the subsequent model-based planning using a physical simulator. So such kind of system can generalize from that single example and then trying to perceive the novel scene of a different object and trying to apply the same skill to that. And all of this relies on 3D reconstruction of the object so that we can get a geometric shape of it. And second of all, relying on a non-physical model that allows us to simulate the rigid body dynamics of it so that we can test whether a particular hanging motion is stable or not. So such kind of thing allows you to generalize to all different kind of objects, including different kind of mugs or different kind of measuring cup. To really showcase the generalization capability of this kind of system, we pick a data set of different kind of alphabetical shapes. And then here you can see the algorithm is automatically picking different grasping poses, different hanging poses, depending on the global shape of the alphabetical shape, and then trying to successfully hand them onto the mug tree. And all those kind of things does not require a non-physical model of the object because you can perceive that using 3D reconstruction to recover that, and then using a physical simulator to simulate the dynamics of it. And then those things are made fast based on the visual guidance from a pre-trained vision model. So here's some comparison with other alternative approaches. So for example, if you directly do policy learning without any visual guidance, and then you get something like a 0% because we only have one single demonstration. If you augment the system with the visual correspondence map that I've been showing you into the policy learning framework, you get slightly better accuracy, like a 24% in terms of success rate. And our system gives you 93% in terms of overall success rate. And here the idea is you use visual pre-trained model as a guidance for a model-based planning approach. But visual pre-trained features or other kind of data-driven learning can be helpful in other ways. For example, in facing with scenario where you don't exactly know the physical dynamics of an object. For example, if you want to operate a coffee machine, then this requires you to understand the geometric constraints in between the handle part and the handle part of the coffee machine and also the body. So this is something that we do not know. We cannot directly annotate. So here you can use learning to help. And in this work, we're demonstrating how you can learn such kind of constraints over hand opening motions from 10 human videos of operating on this particular coffee machine, and then generalize the system to different kind of coffee machines with diverse set of background objects. And again, all the systems, they start with perceiving the scene, trying to localize where the object is you care about, and then trying to make, you use the visual pre-trained feature to help you to generalize to the motion of opening this drawer, opening this coffee machine. And all of those kind of things are done by learning from just 10 examples of operating on a particular coffee machine, generalizing to all different kind of scenarios. So here is the quick summary for this part of my talk, where I talk about one-shot learning or very few-shot learning of generalizable actions, where the advantage here is you can really learn from one or few demonstrations and generalize to different objects and different kind of environments. And then the principle here is to combine visual representation learning and physics models with a neuro-symbolic constraint optimization framework, where the neural network can serve as a guidance or as learning part of the dynamics that you do not know how to exactly model to write down in analytical forms in your physical model. So with this kind of approach, now we can start to make progress on the original problems that motivate us to think about this, like the ABC pickup games. So here I'm showing you some examples where I'm teaching the robot one demo per skill about how you use two sticks to rotate an object on a table and to push an object on the table to the side of the table, and then trying to lift it up. And then I show the system can automatically generalize and compose those skills in novel ways to solve a real ABC pickup game using these two sticks to pick up a D shape on the table. So in this particular case, this is an object they have never seen before. And apparently, the system needs to jointly optimize for where do I want to make the contact, if I want to rotate it, by how much degree I want to rotate, by how much distance I want to push, and then finally lifting it up. Of course, this is still far away from really the dexterity of humans in manipulating all different kind of objects, whether deformable or fluids. But I believe this is an important and promising framework to be extended to handle that kind of generalization and composability of physical actions. So far I've been talking about learning relatively short horizon skills and composing them in novel ways to solve novel problems. So next, let's talk about how we can really extend such kind of framework to solve relatively long horizon planning problems, such as kitchen cleanup problems, where the time horizon of your plan exceeds from a very few seconds to actually minutes, and then eventually maybe hopefully to hours. So I'm going to start with talking about the problem setting we have. So we assume that our system have access to some human-collected robot trajectories and some language and narrations with it. So in this case, let's say we have collected some data. We are teleoperating the robot, trying to move the robot and trying to pick up different kind of objects and do manipulation with them. We assume that such kind of trajectory is segmented, and then annotated with some language and narration, such as from the beginning to this second, we are grasping the dish soap, and then from here to there, we're pouring the dish soap onto a plate, and then finally, we're placed the dish soap back onto the counter. And then we focus on how we can build a system that can learn from such kind of data with the goal of making long horizon plans to unseen states and also novel goals you have never seen before. So what do I mean by that is, for example, if you consider a different initial states, let's say in this particular case, the goal is put a clean plate on the dish rack, but currently there's no dish soap on the plate, but the default set has already been turned on. So this is a scenario that I've never seen before during training time. And our system is able to recognize such kind of state and then think about what are the actions they need to do. Like they need to first pour some dish soap onto the plate before they wash it, and then they can execute this wash motion and then place it back onto the dish rack. Such kind of capability is also important if you. Oh yes.
The plate doesn't look like it was properly cleaned.
Yes, that's true. Yes, that's a good take. Yes.
So it's not sensing what's happening with the plate, or it doesn't know, or what's the problem?
I think we are not collecting probably enough data trying to train this particular policy, and then that because we need to also randomize like how much amount of dirty objects are there on the plate, and that's kind of thing that are blocking the system from being able to totally generalize to all different kind of scenarios. Yes, but the system itself is reactive, actually perceiving the thing. So in theory, you can do it. And then this kind of capability is also important if you think about partial observability. So in the particular scenario, let's say my goal is to put the plate onto the rack and I want to clean the counter. So originally the counter looks clean to you, but after you trying to move the plate from the counter to the dish rack, then you can see, oh, there are actually some dirty pieces on the table. So now the system needs to re-perceive the thing and then think about what they need to do in this environment. In the particular case, you're using a piece of cloth trying to clean up the counter. So the overall idea of this framework is trying to use language to help us make sense of a long horizon plan that a human had been teaching the robot during training time. So what we do is we're developing a learning algorithm that look at the training trajectories, including the image and action data, and as well as the language narrations, trying to build a neuro-symbolic concept model around it, including what are the state features you care about, how to recognize them from data, and then think about, what are the actions there, including recognizing, what are the preconditions, what are the post-conditions of them, and also how I can execute the constraints by solving the constraint optimization problem. So I'm going to first start with, suppose that we already had such kind of neuro-symbolic concept representation for the original domain, how can we make planning with it? So now let's say we have an environment, and it's a state that we can observe, and also a goal in that natural language form. The first thing we can do is that we can use the state feature recognizer to recognize all the state features that are relevant in this task, including recognize there are objects there, and this is a plate, and the plate does not have soap on it. And then the faucet has not been turned on yet. And also, there's a counter, and then the object is not at the edge of the counter. And then this will form an abstract state representation, which allows you to do, search on. So you think about the action model allows you to predict the effect of an action before you execute this action in the physical world. In this particular case, say I want to do the pour soap motion, then after execution, there will be soap on top of the object. And this will give you, make a prediction about what are the new states after executing this action in the same abstract state representation space. You can do a similar thing for different actions, in this case, push the plate. And then you can enumerate, the other possible actions and then think about what will be the effect of it. And you can do that recursively. So the goal of this original task can be translated into some logical statement about a particular state. In this case, I want to find two objects x and y, such as x is a plate, x is clean, and y is a dish rag, and also x is on top of y. So with that, you can, trying to do this kind of search until you have to find a sequence of action that will yield a state such that that kind of statement is true. So in order to obtain such kind of model that allows you to do such kind of planning, we have our learning algorithm working in 3 different stages. So the first stage is we're using large language model to generate a structure based on the language annotation we have. So basically, you think about this as a code generation procedure. So it takes as input, all the language instructions that a human have given to the robot, and then trying to identify important features to keep track of, and also the preconditional effects of all the action being performed in the environment. So it is important to know that although large language model, they can write down some code in some human interpretable forms, like has soap, or on the edge, or there's an action called wash. But really, those kind of terms, like what does it mean by has soap, or what does it mean by on edge, is not really interpretable to a machine. So this means that we need to do the grounding problem, which is trying to ground all those action and state features onto the visual perception and also the robot action data. So again, we do that in 2 steps. The first step is we learning the action body part. Basically, what are the constraints we need to satisfy? Using the set of methods we talked about before, identifying the contact happening between different objects, learning the corresponding grasping pose if the contact is between the robot arm and also the object, and also the placement pose if the contact is happening between the object and another object. And then in some cases also trajectories, like trajectory for tuning up the faucet, for example. The next part is learning the state features and understanding the transition models behind it. So here I'm giving you a particular example. So this is a state trajectory that we observed in the training data. We have the before state, we have the after state, and we have some annotations about it, such as if the object has soap on it before, then afterwards things will be cleaned. So now the job is want to understand what does it exactly mean by has soap, what does it mean by clean. And you can immediately see that this actually is the same problem as we have seen before in the visual question answering setting, but just extended with a temporal axis. So let me quickly recap how we can do that. So we can have the object segmentation for the object we care about, like in this case, let's say a plate, and then we can have the state afterwards. We'll have 2 neural networks associated with has soap and clean, these 2 concepts. If you apply them on top of the feature before and after the execution, you get some probability, and you can evaluate whether this statement is true or false. And in this case, the probability that this particular statement, if A then B is true, can be computed as the probability that B is true or A is false. And this will give you some score, like let's say 0.98. Because this is actually a demonstration trajectory, so actually know this particular transition model should hold, should be true, given the trajectory you have. So you can use the true as the ground truth label to this question, and then trying to do gradient-based update to update the weights of Hassel recognizer and also the Kling recognizer. So after obtaining those kind of models, including the action body, the preconditions, the effects, and also all those kind of state feature recognizers, now you can use them in novel scenarios like given new states and the novel goals, and you can have a planning algorithm give you the robot action to take. Another improvements that we made in this particular paper is that we show you can also make the planning faster by automatically compute approximated value function based on the compositional structure of the environment of all different kind of actions by just analyzing how different actions depend on each other. So such kind of computation is only known to be true or can work for purely discrete planning problems, and we are able to extend it to continuous value states, such as objects have poses, or they even have like a latent neural network features. So how would this really compare with other approaches that people have been thinking about doing this kind of long horizon planning problems? So here we're doing a comparison between our framework and the vision language model-based approaches for long horizon planning. So here we're using the environments that we build, which is a little boiling water domain where we have different kind of objects on in the environment. And then in order to do that, you need to place the kettle into the sink and then move away and then move the faucet head of the faucet towards the sink, and then you need to turn on and off the faucet, and then maybe there are some other objects that are blocking you currently on the stove. You need to move them away before you can actually place the kettle onto the stove, things like that. So one of the state-of approach to accomplish this kind of thing is to say we do that in 2 stages. We giving the current image observation and also the language goal into a vision language model, such as GPT-4o or GPT-4v, and then it outputs some language commands, which will be executed by a language-conditioned robot policy. And then here, for the vision language model, the challenges are, first of all, if you're directly memorizing training trajectories, this will not work because you will be facing novel situations you have never seen before. And also, the error will accumulate because this actually requires tens of steps in order to accomplish the final task. And this also requires you to reason about, understand geometric constraints, such as some objects blocking your way on the stove. In contrast, our model have this planning-driven approach. We have the state, we have the state abstraction, and then it is used as an input to a planner and output control commands. So we're systematically evaluating the system using the following setting. We are collecting training data in exactly the same initial state where the objects are placed roughly at the same location. And all the object states, such as the faucet turned on or off, is exactly the same state. And then we're generalized to novel scenarios that we've never seen before, such as there might be objects in a different location, or maybe the faucet is at a different location and they may be having different states. Actually, if you measure the end-to-end success rate, none of them can be really solved. None of the 6 situations can be solved with a vision language model without any additional fine-tuning. And our model, using the same kind of principles, but by integrating large language models to help you to analyze, the understanding the state feature and action relations, and also doing a bit of like additional learning for actions and state recognizers, they can give you, success rate, which is in this particular case just 100%. It works for all 6 cases we tested it on. So in the particular part, I'm showing you, how you can really integrate, language, vision, and action data, trying to build a system that can learn, reason, and plan using neuro-symbolic concepts. So overall, I've been showing you how this kind of framework enables you to do more data-efficient learning, such as learning visual concepts from only 10% of the training data, or learning new actions from single or very few examples. And also have stronger generalization to different kind of objects or unseen states or novel goals. But so far, all those kind of things, they still only work for a particular relatively small domain, maybe in a particular house or maybe in a particular kitchen in this particular example. So if we want to move forward, I believe we want to, really trying to think about how we can scale up this kind of approach to be a foundation model for reason and planning, and this is something I'm willing to do in my future work. So in particular, I'm interested in building this approach for a compositional foundation model for reason and planning purposes. So if you think about the original model that we have features and action models, and then some of them are associated with neural networks, such as recognizing the state of an object or identifying a relationship, or trying to find values that satisfy a particular constraint. If you want to improve the broader coverage of this kind of system, now I believe you need to have a model generator that can generate a features and action model of interest given the novel situation, and also being able to do all those kind of recognition and also constraint satisfaction solving problems in a broader coverage way. So what do I mean by that is what do we need is some models that can take as input the context, such as what are the kind of objects are there in the environment, and maybe some human instructions, trying to help you identify what are the important state features and what are the important actions you should think about in this particular environment. And then we also want to have general purpose detectors or relationship recognizers or physical dynamics models that takes various kind of sensory inputs and also different kind of concepts you want to recognize or concepts you want to find values for. And then being able to output different kind of things like a Boolean value for recognition problems, poses, trajectories, and forces for different kind of action purposes. In particular, I'm interested in how we can build novel paradigms for training such kind of model from diverse set of data. From some of them can be learned from image-only data, some of them can be learned from video data, and some of them really requires you to actually collect robot action data for, such as for things that requires object dynamics or forceful information, for example. So another thing I'm interested in is you think about how we can build a continual learning paradigm that can start from something that is readily competent, but really being able to expand the competence of the existing system. So one way to think about this is you start with some basic foundation models that is able to do basic recognition or object tracking or basic set of skills, but being able to use the framework I talk about, do reasoning and planning exploration to compose those kind of things to get new experiences. And such kind of new experiments can naturally serve as the data for learning stronger foundation models for the next iteration of learning. It can become the base for the next iteration and get even stronger foundation models. So such kind of thing you can imagine as learning new skills by composing existing skills, but next time you will be more competent about it. I want to build an analogy between this kind of learning paradigm with human cognitive science. So in human developmental cognitive science, people talk about what are the building pieces, or things that people are already very competent in their 6 months, such as they have some basic understanding of objects, they have an understanding of space, there are other agents in the environments, and the agents have their own beliefs, intentions, and goals, and then some basic understanding of logic and number theory. And for human, the important next step is acquire language based on all those kind of core knowledge you have. But as humans, what we can do is we can do a lot of self-exploratory learning afterwards, trying to learn new skills, learn new concepts, or even discover new concepts on your own. And then this is one particular thing that I would really want to do in the future, trying to build on top of the success of existing work that I have been doing. Another future direction I'm very interested in is building the engineering science of intelligence. So this involves answering question about 2 aspects. The first one is on the computation aspects, to what degree can neural networks reason and plan? And also, how does compositionality, those such kind of factorization structure, actually improve the overall sample complexity of systems? On the problem distribution side, I'm interested in how can we parameterize the practical hardness of planning problems. And actually, Neuro-Symbolic framework gives you a lot of evidence and then frameworks to talk about such kind of questions and then suggest solutions to model such kind of problems. For example, if you talk about such kind of discrete logical reasoning structures, in the past I've been studying or answering questions such as, first of all, can we train a transformer to do these kind of things? In my early paper in 2019, we showed that this is actually possible, but with certain limitations due to the computational structure of transformers. And recently, we start to make progress on how much data do we need to train such kind of system. And more recently, I'm interested in how you talk about the parameterize the circuit complexity by trying to do program analysis, trying to understand the symbolic structure of a practical problem, and building connection with that, between that to practical neural network-based learning problems. Here, the principle is using symbols to describe problems and also describe computation, and then trying to think about how we can develop theory around it. And in the future, I'm very excited about extend such kind of results to continuous domain to think about reasoning and planning under uncertainty, and also think about AI alignment problems. Finally, I'm also interested in building computational models for cognitive science purposes. This includes answering questions like how humans could learn compositional structure from data, how humans actually leverage compositional structure to learn new things fast. In the past, I've been primarily working on learning syntax and also learning structures for writing systems. And then, on the other hand, I'm also interested in how humans can make decisions in physical environments. And then recently, we are developing some, physical puzzle games that we ask human sectors to play, and then trying to model their behavior in playing this kind of games and how they learn skills, how their learn skill being able to generalize from one single example to different kind of scenarios. And here we're using neuro-symbolic techniques as a controllable and interpretable model for us to better understand human intelligence. And then moving forward, I'm very excited about this kind of approaches in understanding human language acquisition, language emergence and evolution, and also abstraction and planning in human cognition. So if I have the right amount of resource, I'm also interested in understanding, for example, how huskies can make decisions in such kind of physical environments for sure. So with all that, I'm going to give you a quick summary of my research I've talked about. I started with some theoretical understanding of computational complexity, sample complexity, and verifiability, and also parameterize the hardness of practical problems. Using that kind of insight to develop better algorithms for reasoning, constraint solving, and planning purposes. And based on top of that, deploying such kind of algorithm in practical systems for visual question answering, for action selection in physical robots, and also for cognitive modeling. And using those kind of practical system building to inform us to build more relevant theories around it. I would argue this is a new bet for building general purpose intelligence system that we can really do in academia that tries to bridge between building intelligence systems and then from our understanding of intelligence, either from the theoretical aspects of it or from the cognitive science aspect of it, and then trying to build a bridge between them. So with all that, I want to give my acknowledgement to all the funding agencies, industry companies, and advisors and collaborators, and also all my mentees that contributed to some of the work that I mentioned in this particular talk. And then with all that, I'm going to thank everyone for listening. I'm happy to take questions.
So there's a large body of previous work on your symbolic AI. How does this relate to that?
Yes. So first of all, we are definitely taking a lot of inspiration from classical, Neuro-Symbolic, including some of the work you've been doing, trying to focus on, trying to formulate the, for example, probabilistic logic, how the formalism of it, and also we're taking, for example, a lot of the work in prob log, data log, those kind of formalism, trying to, make the entire thing theoretically sound. So the additional thing that we do, I think, is the new thing that we can do using the current era of technology is. First of all, now we have better models to construct the symbolic model of it because now we have better program synthesis techniques and also more large language model driven techniques for synthesizing the structure of the problem, in addition to being able to learn everything from scratch. And then second of all, one way to think about a lot of the work I've been doing is you take inspiration from all those previous work and trying to think about how can you use neural networks, more than deep neural networks, and then or pre-trained networks in novel ways to parameterize certain probability distribution inside it, but putting them together in a theoretical framework deployed, in good old AI era, and then trying to solve novel problems of interest.
So, do you think that having a symbolic layer using concepts that are identified using neural networks is the best approach to combine the two?
I would say I personally believe in that for two reasons. The first one is if you think about all of the practical problems, the underlying problem, they have some structure. For example, in physical environments, we naturally have the sparsity in your transition model just due to the physical dynamics we have. And then the best way that we know of to leverage such kind of sparsity and factorization structure is by building some kind of like a symbolic layers on top of some like neural network that capture all the low-level details. From another perspective, which is from the data usage perspective, I think this is a good use of using language data to suggest some of the high-level structures, and then using other visual grounded or action data, trying to figuring out all the details. So I would say this is a natural factorization, naturally factorize the use of your data as well. So from this perspective, I believe this is the right way to go.
Anyone else?
Yeah, I'll ask a good question. Yeah, so a lot of like in the examples in the beginning were like answer a question about an image or something. But my understanding, kind of like, if I want to ask a question about a piece of text, I don't need symbolic AI. I can just train a big transformer. And so kind of what's different about these domains that makes us need these kind of symbolic, kind of more complicated techniques?
I think I think the fundamental issue. Okay, I would say first of all, the fundamental issue is that for certain domains, including robots where you have dynamic physical dynamical systems, it's usually very hard to collect a good amount of data, and this is even harder when you have uncertainty and you want to think about how you do exploration in the environment and so on. So that's where I think model-based approach is gonna be more relevant there. And then I think the second reason is that although for sure you can use learning just to solve a lot of things, if you can collect a lot of data. Actually, one way to generate it is by using this kind of symbolic model to to synthesize possible reasoning chains about how to answer questions. I think for example, Renjie here is doing some work about that, about distilling such kind of programmatic execution onto large vision language model to do things. But I guess the question is whether it is the most efficient way to do that. From a perspective of in practice, a lot of especially in robotics, I would say, a lot of the problems are very, very hard. So that finding a solution at a training time is actually very hard. And second of all, they're really, really diverse. This means that I believe, at least, trying to enumerate all possible problems that a robot would ever met at training time in the factory, and then just train the system on explicit data on it is probably not the most efficient way to do that. And then that's why we need to think about what's the kind of thing you want to do at training, and then maybe doing at test time, also doing a bit of test time inference, trying to augment the system. Yeah.
Your premise is false, though. LLMs are not enough to understand things. There are countless examples where they can.
Well, and text like good enough might be good enough for like generating ad copy on Amazon, but like it may or may not, but probably not good enough for like doing.
Generating ad copy is actually very subtle.
I know. I'm being facetious, but it seems strictly harder to pick things up.
It's not solved, but it's pretty good, right?
If you're okay with hallucinations and making stuff up, then
I have a question for the speaker.
Hi, thank you for your talk. And I was curious if you see a connection between kind of the sort of like segmented way your neural networks are architected and like mixture of experts models, and whether you think there's some deeper connection there.
So what's the model we're talking about?
Mixture of experts.
Oh, okay, I see. Yeah, so that's definitely very interesting. I think probably one deeper connection between those kind of having separate neural networks to do something is model merging. So basically, something I really want to do is after having trained individual neural network trying to do individual tasks, you also want to be able to I would say like merge or compress all those models to be a slightly bigger model, so that you can also leverage data across different tasks to get better generalization. So that's I think that's one important thing to do in a continual learning situation. And then I would say that is still very much in the research frontier, how you can do that, at what frequency, how you actually do the model merging so that you do not have the catastrophic forgetting, those kind of issues. And then there are a lot of interest there, I think. Yeah.
Hi, so I had a question about the architecture of the neural networks. In neuroscience, we're getting a better understanding of different neural circuits and also just different parts of the brain that are involved in, say, identifying something or doing something. So from findings in neuroscience, has that informed how you decide to architect, say, mixture of experts things or segmented neural networks, and how so?
Right. I would say the primary inspiration that I took is primarily from cognitive science, but we're definitely recently seeing a lot of good, interesting connections between computational cognitive science and also cognitive neuroscience. One of the important things that people see recently in neuroscience study is when people are trying to solve problems, even if the problems themselves are describing language, actually they are not necessarily using their language section of their brain trying to solve that problem, but instead there's a different area in the brain got activated. So this is especially true if you're if your question, for example, contains reasoning about reasoning about numbers or reasoning about physical situations, like if I'm asking you, imagine there's a kitchen and then what do we do there, things like that, and then you will see different kind of areas being activated other than the language area. So this means that, to some extent, probably language is not exactly, this is just, based on very coarse fMRI level study, not really at the neurocircuitry level, but there's, some interesting, people start to think about maybe language is not really exactly the way, or human, like a natural spoken language is not really the way that people structure thoughts, but instead there is another kind of like a language of thoughts, but not in the form of human language that connects to the human language. You can translate in between them. And also, it connects to other areas of your brain, like being able to do physical simulation, being able to make plans, and being able to retrieve, previous episodical memory information, whatever. So I think that's a very, very interesting finding recently we got, and then that definitely motivates some of the design here, such as the concept is not really living in the language space, but really it's something that you can talk about, something you can see, and something you can act on. Yeah.
Thank you.
Can you comment a little bit about how error might compose in some of these neuro-symbolic things, right? That would be breaking everything into these propositions. I'd be concerned that that might explode. In some of the, you discussed this a little bit in some of these longer term planning things, but even just, if you could describe that a little bit, that'd be great.
Right. Okay. I think personally have two takes on it. The first one is I think even if you are using such kind of neuro-symbolic way to structure a computation, you still want to make sure the entire system is end-to-end optimizable. That is, in the particular visual question answering case, even if you're composing all these neural networks, but you are not training them separately, but they are trained end-to-end from just input and output data. And then we do the kind of the similar thing for robotics planning stuff as well. That kind of help you to a certain extent, you reduce the amount of error accumulation because all the modules, they're jointly optimized. The second thing, which I think is very interested in, I'm very interested in study and then building, is having those individual modules maintain their own uncertainty about their prediction, and then being able to reason about those kind of uncertainty, because in practice, you never need a very, very accurate physical model to do a lot of things. In controls, people talk about, multi-layered system, where at the higher level, you need relatively coarse model. At the lower level, you need more fine-grained model and things like that. And then I think how we actually model and correctly model the uncertainty and then think about how they propagate and how we reason about the required level of precision in prediction is something we need to do.
The first example, if we train everything end to end, my primary concern would be about transferability, right? Because okay, cool.
Yeah.
All right.
Sorry, don't you lose the compositionality when you do the end-to-end optimization?
Yeah, it's the same.
I guess there's the identifiability problem to what extent. So if you think about if all the places they are on counters, then if you optimize things end to end, then when you're recognizing place, you probably rely heavily on the fact that the object is on the counter. So, but if you have cross-situational data where you have places at different locations and so on, this will help you to address that a little bit. Yeah.
Yeah, I think there was enough questions. So let's thank the speaker again.